Hey cosmic explorers, and welcome back to Cosmic Enigma, your portal to the wonders of the universe. Have you ever gazed at the night sky, perhaps through a telescope or even just with your imagination, and wondered why galaxies aren't all the same? From the majestic spirals that resemble cosmic pinwheels, to the smooth, ethereal ellipticals and the chaotic, vibrant irregulars, our universe is a breathtaking tapestry of galactic forms. But why this incredible diversity? What cosmic forces sculpt these islands of stars into such wildly different sizes, shapes, compositions, and levels of activity? Get ready to embark on an exhilarating journey into the heart of galactic evolution, exploring the astrophysical mechanisms that make each galaxy a unique masterpiece. The sheer scale of galaxies is mind-boggling, ranging from tiny dwarfs to colossal giants. This isn't random. It's a story written in the very fabric of the early universe, largely dictated by the mysterious influence of dark matter. Dark matter, an invisible substance we can only detect through its gravitational pull, acts as the universe's scaffolding. It forms vast, intricate webs and halos, pulling in ordinary matter like gas and dust. The initial clumps, or overdensities of dark matter in the early cosmos determined the gravitational potential wells where galaxies would eventually form and grow. Galaxies don't just spring into existence fully formed. They evolve and grow over billions of years. One primary mechanism is accretion, the continuous inflow of gas and smaller clumps of matter from the surrounding cosmic web. This slow, steady diet helps galaxies accumulate mass. However, the most dramatic growth spurts often come from more violent events. Imagine galactic cannibalism, where larger galaxies literally gobble up smaller ones. Our own Milky Way is a prime example, currently absorbing the Sagittarius dwarf spheroidal galaxy, a process that has been ongoing for billions of years and will continue to shape our galaxy. Then there are mergers, the spectacular cosmic collisions between galaxies. When galaxies collide, they don't just bounce off each other like billiard balls. Space is incredibly vast, so direct star-on-star collisions are exceedingly rare. Instead, the gravitational forces between the two galaxies distort and intermingle their gas, dust, and stars. If they don't have enough relative momentum, they merge into a single, larger galaxy. This process is often described as the lifeblood of the universe because it's a fundamental driver of galactic evolution. These mergers have profound consequences. The compression of gas during a merger can trigger intense bursts of new star formation, creating dazzling regions of bright, young stars. They can also feed the supermassive black holes at the galaxy's centers, leading to powerful outflows. The result of these growth processes is an astonishing range of sizes, from tiny dwarf galaxies containing only a few 100 million stars, like the Small Magellanic Cloud, to colossal giant ellipticals, such as M87 in the Virgo cluster, which can boast over 1 trillion stars and span hundreds of thousands of light years. The size of a galaxy is a direct reflection of its initial dark matter halo and its subsequent history of accretion and mergers. The visual diversity of galaxies is perhaps their most striking feature, famously classified by Edwin Hubble in the 1920s. His tuning fork diagram categorized galaxies into 3 main types: spiral, elliptical, and irregular, with various subtypes. Each shape tells a story about a galaxy's formation history, its internal dynamics, and its environment. Spiral galaxies, like our magnificent Milky Way, are cosmic pinwheels. They feature a flattened disk with prominent spiral arms, a central bulge, and often a surrounding halo. These arms are not rigid structures, but rather density waves, regions where gas and dust are compressed, triggering intense bursts of star formation. This is why spiral arms glow brightly with hot young blue stars. Spirals are rich in gas and dust, the raw materials for new stars, and are characterized by ongoing star formation. Their rotation speed and the amount of gas available affect how tightly or loosely wound their arms appear. Many spirals, including our own, also possess a central bar structure, which acts like a cosmic conveyor belt, funneling gas towards the galactic center and potentially feeding the central black hole. Elliptical galaxies, in stark contrast, are smooth, round, or cigar-shaped blobs. They lack the distinct spiral arms and flattened disks of their spiral counterparts. Ellipticals are typically dominated by older, reddish stars with very little gas and dust, meaning they have minimal ongoing star formation. They are often the result of massive galaxy collisions. When two gas-rich spiral galaxies merge, the violent interaction can disrupt their disks, randomize stellar orbits, and consume or expel most of their gas, leaving behind a smooth, featureless elliptical remnant. These are often found in the crowded centers of galaxy clusters where mergers are more frequent. Irregular galaxies have no clear, defined shape. They are often chaotic, clumpy, and appear as a mess of stars, gas, and dust. Many irregulars are thought to be the result of recent gravitational interactions or collisions that have distorted their original structure. Others might be primordial galaxies that haven't yet settled into a stable form. These types were super common in the early universe, before cosmic structures had fully matured and settled down. They are typically rich in gas and dust and exhibit vigorous star formation, often in localized bursts. Beyond these main categories, there are also in-between types and peculiar galaxies, such as lenticular galaxies, S0, which have a disk and a bulge but no spiral arms, or stunning ring galaxies, formed by a smaller galaxy plunging directly through the center of a larger one, creating an expanding wave of star formation. Each unique shape is a snapshot of a galaxy's dynamic journey through cosmic time. What a galaxy is made of, its ingredients, profoundly influences its appearance and evolution. The primary raw materials for new stars are gas and dust. Gas, predominantly hydrogen and helium, collapses under gravity to form stars. Dust, tiny solid particles, plays a crucial role in shielding star-forming regions from harsh ultraviolet radiation, allowing them to cool and collapse more efficiently. Galaxies rich in gas and dust, like spirals and irregulars, are typically vibrant with ongoing star formation. Then there's metallicity, a term that can be a bit misleading. In astronomy, metals refer to any element heavier than hydrogen and helium. These heavier elements are not primordial. They are forged inside stars through nuclear fusion and then dispersed into space when stars die, either through supernova explosions or stellar winds. This process of cosmic enrichment means that successive generations of stars are born from gas that is progressively richer in metals. Why does metallicity matter? It's critical for star formation. Metals act as coolants in gas clouds. They efficiently radiate away energy, allowing the gas to cool down and clump together more easily under gravity. Without sufficient metals, even a large cloud of hydrogen and helium might struggle to cool enough to collapse and form new stars. This is why the very first stars in the universe, formed from pristine hydrogen and helium, were likely much more massive and short-lived than stars today. A galaxy's metallicity, therefore, is a direct indicator of its star formation history. Galaxies with low metallicity often have very little ongoing star formation, even if they have some gas, because that gas cannot cool efficiently. A galaxy's star formation history, how quickly and efficiently it converts its gas into stars, is a huge part of its identity. This history dictates its overall brightness, its color, blue for young, hot stars, red for old, cool stars, and its future evolution. A galaxy that has rapidly consumed its gas in a burst of star formation might appear blue initially, but will eventually redden as its massive stars die off, leaving behind a population of older, redder stars. Understanding these ingredients and their evolution is key to deciphering the life cycle of galaxies. Galaxies are not static collections of stars. They are incredibly dynamic systems, often driven by powerful processes at their cores. Many, if not most, large galaxies harbor a supermassive black hole at their heart, millions to billions of times the mass of our Sun. These black holes are usually dormant, quietly residing in the galactic center. However, when gas and dust fall into their gravitational grasp, they can become incredibly active. When a supermassive black hole actively feeds on surrounding material, it becomes an active galactic nucleus, AGN. As matter spirals into the black hole, it forms an accretion disk that heats up to extreme temperatures, emitting vast amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. These AGNs can shine brighter than the entire galaxy they reside in, making them some of the most luminous objects in the universe. Quasars, for instance, are the most extreme and luminous type of AGN, often found in the early universe, indicating periods of intense black hole growth. The energy released by AGNs can also drive powerful outflows in jets, which can profoundly impact the surrounding galaxy, sometimes even suppressing star formation by heating or expelling gas. Then there are starburst galaxies, regions or entire galaxies experiencing an intense, frenzied burst of starbirth. These are cosmic fireworks shows, where stars are forming at rates hundreds or even thousands of times higher than in a typical galaxy like the Milky Way. Starbursts are often triggered by galaxy interactions or mergers, which compress gas clouds and lead to rapid collapse and star formation. The intense radiation and supernova explosions from these newly formed massive stars can also drive powerful galactic winds, expelling gas and heavy elements into the intergalactic medium. Interestingly, AGNs and starbursts are often linked, especially after wet mergers, collisions between gas-rich galaxies. The same influx of gas that fuels a starburst can also feed the central supermassive black hole, causing it to light up as an AGN. This suggests a profound coevolution between a galaxy's central black hole and its overall star formation activity. The black hole's growth and the galaxy's star formation are deeply connected, influencing each other in a complex cosmic dance. Studying these active phases provides crucial insights into how galaxies regulate their growth and evolve over cosmic time. A galaxy's fate is not solely determined by its internal properties. Its cosmic neighborhood can drastically change its evolution. Galaxies are not isolated. They reside in a vast cosmic web, forming groups, clusters, and superclusters. The density of galaxies varies enormously across the universe, and this density plays a critical role in shaping galactic diversity. Galaxy clusters are like crowded, bustling cosmic cities containing hundreds to thousands of galaxies packed into a relatively small volume. In these dense environments, you typically find a higher proportion of smooth, old elliptical galaxies and fewer gas-rich spirals. Why? The harsh conditions within clusters can quench star formation in infalling galaxies. One key mechanism is ram pressure stripping, where the hot, diffuse gas permeating the cluster, the intracluster medium, literally strips away a galaxy's cold, star-forming gas as it moves through the cluster. This process effectively starves the galaxy of its raw materials, halting new star formation and leading to its reddening over time. Another powerful environmental effect is tidal forces. The immense gravitational pull from the cluster's central potential well, or from close encounters with other massive galaxies within the cluster, can exert strong tidal forces on a galaxy. These forces can rip stars, gas, and even dark matter right out of a galaxy, creating long, ethereal tidal streams that stretch across vast distances. This process can significantly alter a galaxy's morphology, sometimes transforming a spiral into an irregular or even contributing to the formation of an elliptical. This highlights the heredity versus environment dilemma in galactic evolution. Are galaxies born different, or do their surroundings fundamentally change them? The answer, as with many complex astrophysical phenomena, is both. A galaxy's initial conditions, set by its dark matter halo, provide its heredity. However, its interactions with other galaxies and the dense intergalactic medium in its environment profoundly modify its evolution, shaping its size, form, and activity. Understanding these environmental effects is crucial for building a complete picture of how the universe's diverse galactic population came to be. The incredible diversity of galaxies we observe across the cosmos is not the result of a single factor. but rather a magnificent symphony of interconnected cosmic forces. It's a grand interplay of initial dark matter conditions, the relentless pull of gravity, dramatic galactic collisions and mergers, intricate internal processes like star formation, and the powerful feedback from supermassive black holes, and the profound influence of their cosmic neighborhood. Each galaxy is a living, breathing entity, constantly evolving and interacting with its surroundings. Astronomers, armed with cutting-edge instruments like the Hubble Space Telescope and the revolutionary James Webb Space Telescope, are continuously unraveling these mysteries. JWST, with its unparalleled infrared vision, is particularly adept at peering back in time to study the very first galaxies, revealing how they formed and evolved in the early universe, a period when many of the processes we've discussed were far more intense and frequent. The universe is a dynamic, ever-evolving masterpiece, and every galaxy, from the smallest dwarf to the grandest elliptical, tells a unique and compelling story of cosmic creation and transformation. What's your favorite type of galaxy, and what cosmic mystery about them fascinates you the most? Share your thoughts in the comments below. If you've enjoyed this deep dive into galactic diversity, please like this post, subscribe to Cosmic Enigma for more astronomical adventures, and share it with fellow cosmic explorers. Your support helps us continue to bring the wonders of the universe closer to you.